So, what you have to remember is when you use your central limit theorem, that your mean stays the same for your sampling distribution. You're doing a bunch of samples. You're recording the mean of those samples and then the mean of those means. So you're taking like the averages and then you're taking one large average. And basically, that's what you're doing, your arithmetic mean. What happens is it pulls your standard deviation in a little tighter. Now, and like I was saying to Gunnar, when we graph this, even though your graphs are real narrow, we still graph it wide, we would be able to fit no information on here. So if we still give it a little distorted look to it, this is the way we can fit all our stuff on here. But realize that this is what it's doing here. It's pulling your standard deviation in a little smaller, making it a little tighter. And we saw that when we use the central limit theorem, it does create a normal distribution if we're over 30 for your sample size, or if your population is already normally distributed. So those are two important things that we learned from your central limit theorem. So all you had to do basically was, just give me a little sketch. The one was C, because the first one, if you looked at it, your standard deviation was 11.19. C was 1.19. It took the standard deviation of that divided by the square root of 100, which shrunk this down. It gave us the smaller standard deviation, and it made your graph narrower, not wider. It pulls it in together. Everybody okay with this? It was just a little exercise in plugging this into your formula. That is really the only difference that you will notice. Okay. Well.
Why do you multiply by 3 at the end?
Why did I multiply by 3?
Just to find the end product of her sketch. You're writing the end number on the way.
What did it say in 15?
You know what I mean? Instead of adding, I don't know.
Yeah, that's why.
But this is how she used that. That's what she did.
She used sound deviation to subtract 3 times.
Wait, a little sense of it. It just like gave you a little spread here by doing this. Like it shows you where does this go to. No, you don't have to do that at all. And 18 and 19, shh. Remember, the mean does not change. This is very, very important right here. As your sample size increases, your standard deviation gets smaller. It decreases. And that makes sense. Because if you divide by the square root of 9, or you divide by the square root of 25, you're dividing by 3, you're dividing by 5. When you divide by a larger number, don't you get a smaller number? So this does make sense when we do this. Okay, so everybody okay with this? Okay with this part so far? Okay, so we're going to, on page 251, we're going to start using your probabilities with your sampling distribution. The last one that we're going to do is actually going to compare a population to a sample. But for the next couple of ones, we're just going to work on finding your sample probabilities. They work exactly the same as your other ones. You just have that one little thing to put into your standard deviation. So your z-score formula that said x minus the mean over the standard deviation will now say x minus the mean, sample, these are your sample means, over your standard deviation divided by how many is in your sample size. This is the only difference right here. That's the only thing that you're going to notice that we're going to do. And they're going to give you the mean of your sample means. But the way the problems are worded, you kind of get a good feel for, oh, I got the sample things, because they always tell you random samples of X amount, N amount. They will tell you that part. So let's take one and try this. Okay. You randomly select 50 drivers. So here's your sample space right here. Their ages are 15 to 19. What is the probability that they spend between 24.7 and 25.5 minutes? So probability, you write it the same way. And you guys have to get used to writing your probability statements. That tells you which way your shading is going. So we know we randomly select this, and I think you're going to have to look at your example in the book, and you take your 15 to 19 age group, and you see how many minutes they spend driving. What is their mean driving time according to your chart? There's a chart on 251. 25 minutes. Thank you, Tamara. 25 minutes. They spend 25 minutes driving on the average. Now, they said use your standard deviation to be 1.5. We do this exactly the same way that you did your other one. So when we do a between, we graph, and then we spread it a little wider so this way we can see everything. So 24.7 to 25.5. We want the probability in the in-between. God bless you. Now, I'm going to show you on the formulas, and then I'm going to show you in the calculator, because you can still do this in your calculator. So we're going to take the z-score for when we have 24.7, and we're going to take the z-score for 25.5, and what do when we find the z-scores for these guys, for in-betweens? Subtract what? The areas. Good. So we're going to find their z-scores, and we're going to use the sample mean minus the population mean over the standard deviation divided by the square root of n. So we basically work this the same way. 24.7 minus 25, doesn't this still give us a negative z? Over 1.5 divided by the square root of 50. Okay, so according to them, they worked it all out. So their z-score is negative 1.41. So let's find the z-score for this. Same process. The only thing is we have to change our standard deviation. So we take the x minus the mean over the standard deviation divided by the square root of 50. And this z-score has to be positive, 2.36. Now, we wouldn't have thought they would have been that far away. But what happened is your standard deviation dividing by the square root of 50, that's like 7. Dividing by 1.5 divided by 7 makes it a lot smaller. So we look up both of the areas for these guys. We find your areas, and if you look in your book, you can see they subtracted the areas. So they subtracted the areas, and they found the probability of in between. And they get 0.9116. So the probability that a random sample of 50, these random samples that you're getting, you did a whole lot of these samples. The probability of you selecting one sample of 50 and having them drive between 24.7 and 24.5 minutes is about 91%. You have a strong probability that they'll be driving there. Normally, you would know that anyway. If you looked at your graph, make sense out of this. Isn't it right about the mean? Isn't that where we say 68 point something occurs normally? So if we shrink this down a little bit, doesn't it have to be more than 68? So it's almost, even if you did a plus or minus 1, you're in that zone without even changing your standard deviation. So since we shrunk it down, we got a big chunk sitting right in that middle. Okay, now when you use your calculator, and some of you need to be careful, you're throwing an inverse norm a lot. Inverse norm is only when you want to find that x value, or you want to find your z-score if you use the 0 and the 1 area. But if you use the normal CDF and you use the in-between, I don't think I can pull it up on my calculator, but if you do the in-between, there's your lower, there's your upper, your mean is 25, your standard deviation, let your calculator do this. Just do 1.5 divide by the square root of 50. Do this right in your step, and it will do it for you. So if anybody wants to try their normal CDF, you should come out close to that 9.9116. You won't come out exactly, because your calculator has a nicer way to round than we do. Remember your z-scores? We have to round to 2 decimals to look them up. Your calculator doesn't. So let your calculator do this part right here. And you should come out to be close to that. You try it, Amanda? Not yet? Anybody? 0.9121?
Yeah.
So we're very close to your 0.9116. It's just in the rounding that the rounding is a little bit different. Your calculator is a little bit more exact than we are because we round a little bit less than they do. But this is absolutely doable in your calculator as well. I would let your calculator do this step right here and not you, because if you do it, you're going to have to bring your standard deviation out at least 3 decimals or so. So we see that it works the same, right? Right? It works pretty much the same. Now, in this next one, we randomly select 100 drivers to be in our sample size. Everything else is staying the same. So if I increase to my standard deviation, it's going to change now, because I increased my n from 50 to 100, what's going to happen to this? Not double, but it would increase, right? Okay, what's going to happen to your areas now? I want you to think for a minute. What's going to happen to your standard deviation if I increase this to 100? No, your standard deviation is going to do what now? Shrink. It's going to decrease. So I'm going to be decreasing my standard deviation. Is that what you said? I'm sorry. I thought it was increasing. You know when you stand up here, you get like the voices from, I'm sorry, Alyssa, I'm sorry. So your standard deviation is going to decrease. You're going to pull your curve in a little bit more. Therefore, your area in between is going to be a little bit tighter. So we're going to try this formula. We're going to do this formula with the standard deviation divided by the square root of 100. And if you want to, you can certainly do this on your calculator. Again, I would just put it in your calculator, let your calculator do the standard deviation. You're going to look up your z-scores, you're going to find your areas. Anybody throw it in their calculator? Simran, did you throw it in? Are you doing it? Stay with me here. All right, so what happens to your z-scores is they spread further apart. And then 99, 78, you said?
Yeah.
68?
No, 16, 97.
So look what happened to your area.
I got 97.
97. So, guys, look what happened to your area. Your area increased because your standard deviation got smaller because we divided by the square root of a larger number. So like Alyssa said, your standard deviation will decrease. We'll pull your curve in a little bit tighter. So it's like squishing all that area under a smaller amount of curve. Okay, let's try another one. These really aren't that bad. All right, one more, and then tomorrow we'll do the difference between the population and the sample. The mean room and board expense per year at a 4-year college is $58.50. Remember, this book is quite old. It's no longer that. Trust me, it's no longer that. You randomly select 9. Here's your sample size, guys. 9 4-year colleges. What is the probability? Here's your probability statement that X is less than 6180. So here's your graph. Here's your mean. 6180. We want this. So our probability has to be greater than 50%, right? Okay. We're going to assume they're normally distributed, so that's good because our sample size is small. You need to know this. And it has a population standard deviation of 1125. So all we have to do is plug this into our new formula, find our z-score. So we take the x value, we know we have to be positive, so it's the larger minus the smaller. Divide by your standard deviation, divided by the square root of 9. Now, dividing by 3 is not a very large number, so it's going to change it, but not drastically. So we're going to come up with 0.88. And then you're going to look up your area, and it's your area to the left. Okay? Your area to the left, which is 0.8106. So there's about an 81% chance that the random sample that I select, their mean room and board is less than 6180. Tomorrow we're going to compare the samples to the population.